Hi everybody, I hope this video finds you well. In this video, we're going to do a brief sort of introduction into the sort of concept of counting. In our last video where we talked about the multiplication rule, we saw that things can sort of get messy when you have lots of different ways for something to happen. We did a couple of examples. The first one was one where we were selecting 4 people and we wanted 3 of them to be Democrats and 1 to be Republican. And then we sort of saw that there were 4 different ways for that to happen. We could be like Democrat, 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 Republican, or Democrat, Democrat, Republican, Democrat, and so on. And then we did a second example with free throws where it was about making and missing them. And we saw that sometimes we would have to count all the different ways that somebody might make 2 and miss 1 out of 3. So to get a little better at that and to sort of speed that process up and to see some better ways to handle situations like that in probability, we're going to spend one video sort of talking about counting. Now in mathematics, counting is actually a branch of mathematics called combinatorics. We're not going to go super deep into this. We're just going to sort of give a very surface level discussion so that you guys have the tools necessary for probability. So keep in mind that for this class, you won't be doing a lot of just direct counting like we'll be doing in this video. You'll mostly be using it to do probability-based questions like we'll see in the following videos after this. But for this one, we're going to just focus on this idea of how to get better at mathematically counting things. So the first thing we're going to do is just to get a sort of basic example to get the sort of idea down and see one of the primary operations in counting and how it relates to something we've already discussed for probability. So let's start with this sort of basic example here. So we're going to suppose that you have this favorite restaurant that you like to go to that offers a 3-course meal. And what they do is they have you choose 1 appetizer, 1 entree, and 1 dessert. For appetizers, they have 2 options. You can order a salad or soup, not a super salad, because if you say super salad, it sounds like the salad's going to be really good, and if it's not, you'll be disappointed. So they phrase it as a salad or soup. So 2 options for appetizers. For entrees, you've got 4 options. You can order the chicken, the steak, the fish, or the gluten-free vegetarian pasta. And for dessert, you've got sort of 3 options. You've got cake, sorbet, a moment of panic there. It's sorbet, of course, right? And everyone is like, oh, is it actually pronounced sorbet? No, it's not sorbet. So cake, sorbet, and fruit. Don't know why we have so many little comments here, but then again, why not, right? So we've got 2 choices for the appetizers, 4 choices for the entrees, and 3 choices for dessert. And our question is, if you really like this restaurant, how many sort of different experiences or different meals can you have at this restaurant? So we've got to sort of think about how do you put these options all together. The sort of basic things you should be thinking about is that you're either going to be sort of adding these operations, right? These 2 choices here, these 4 choices here, and these 3 choices here, or multiplying. Now, we're going to relate this to the multiplication rule in probability, so it shouldn't be a big surprise that to figure this out, you multiply. In other words, the way you actually determine how many different meals there are is you sort of imagine how many choices do you have for appetizers, how many for entrees, and how many for dessert. Well, you've got 2 choices for appetizers, 4 for entrees, and 3 for dessert. And we are going to multiply those together. And we're going to see that there's 24 different meals. Now, for some of you guys, you might totally just take this at face value and believe that multiplication is the correct choice of operation there. For some of you, you might be a little less convinced. So let's try to diagram, at least in this basic case, this sort of out so you can see exactly why 24 makes sense. So let's give ourselves a little diagram here, right? There's you, right? You're nice and happy because you're going to your favorite restaurant. You walk into the restaurant and what happens? That you immediately are hit with a choice. They ask you, do you want your salad or soup? So immediately there's 2 different sort of paths you can go down. You can go down the sort of salad path over here or the soup path. Notice that once you've gone down that path, your meal is going to be a different experience because these are the meals where you have salad, these are the meals where you have soup. After you've selected the salad, right, they immediately ask you, what sort of entree do you want? Chicken, steak, fish, or gluten-free vegetarian pasta? So from here, we get 4 more sort of branches, right? We get a sort of chicken branch, we'll start abbreviating, a steak branch, a fish, and a gluten-free vegetarian pasta. Same thing down here, you get a chicken, steak, fish, and a gluten-free vegetarian pasta. So what do each of these represent? Well, this is the route where you order salad and then chicken. This would be salad and then steak. This would be soup and then chicken. This would be soup and then steak. So each of these gives you a sort of different meal through appetizer and entree. Now, we want to also include dessert. We'll do that in a moment. But let's see if you stopped at entree, how many choices there would be. There would be 4 up here and 4 down here. There would be 8. And that would be coming from the 2 choices here times the 4 choices here. 2 times 4 would give us 8. If we go a step further and go from each of these and add 3 options, well, we'd see from the chicken here, we'd have a cake, sorbet, and fruit. We'd have cake, sorbet, and fruit. Cake, sorbet, and fruit. Cake, sorbet, and fruit. It sounds like I'm trying to hypnotize you guys by wanting you to eat cake, sorbet, and fruit, which might just be a symptom of me recording this at like 9:30 and thinking about dessert right now. Same thing down here. We have cake, sorbet, and fruit. Cake, sorbet, and fruit. Cake, sorbet, and fruit. And finally, cake, sorbet, and fruit. So how many options do we have here? Well, we can count. Here's 3. Here's 6, here's 9, here's 12, 15, 18, 21, and 24. So we do have 24 different meals. And our weird little diagram here also shows us what all those meals are. Here's the salad, chicken, fruit meal. Here's the salad, fish, and sorbet meal. Here's the soup, steak, and fruit meal, right? Every one of these paths is a different meal. So this tells you guys one sort of big idea. When you're doing counting, the main operation, the most common way to glue together numbers of options is going to be multiplication. That's really the whole point of this example, to make you realize that when you're counting and you have different choices, different numbers of options, you glue those together via multiplication. All right, let's look at a little bit more advanced of an example where we're going to count things that are way too large to diagram out like this, but we can use the same approach. So let's talk about some passwords, and specifically we're going to think about PIN numbers. PIN numbers, which just stands for personal identification number, is usually like a 4-digit password where the digits are made up of 0 through 9. So what we're going to do is we're going to try to count how many PIN numbers are out there. And then what we're going to do is we're going to look at how many pins there are with different sorts of restrictions. So let's first start by trying to figure out how many pins in general there are. Well, according to this, a PIN is a 4-digit password. So when you're making a PIN number, you make 4 selections. Just like in that previous example, when you're choosing that meal, you make 3 selections. Here you make 4. So how many choices do you have for this first selection? Well, since it's a 4-digit password, you get to choose between 0 and 9. If you think about 0 through 9, there are 10 different selections in there because 1 through 9 is 9, and then the 0 is the 10th. So you've got 10 choices for this first digit. Then for the second digit, you've got 10 choices because it also is a digit. Then 10, then 10. We multiply all those together and we see that there are 10,000 different PIN. So in other words, what we're sort of saying out there is that there are 10,000 different pins out there. So that's pins like 9523 or 5555 or 3320, right? All of those are part of those 10,000 different pin numbers. Okay, now let's do this in sort of a restricted way. Let's now say how many pins are there that do not repeat digits. So now we have this extra little bit of a sort of constraint. We do not want them to repeat digits. So it's still going to be 4 selections. How many choices do we have for the first one? Well, you can choose any digit you like, 10. What about for the second one? Well, for the second one, we're not allowed to repeat digits. So whatever we put here can't be used here. That means we're going to be down to 9 choices. When we go to do this one, we can't choose whatever we put here or here, because then we would have a repeat. So we only have 8 choices. When we get to the last one, my apologies, it's supposed to be in a laser there. And in the last one, well, we can't use whatever we put here, here, or here. So there's only going to be 7 choices here. We multiply all those together and we get 5,040 different pins without repeats. Now, are we shocked that this is a smaller value than this? Of course not, right? If we have this restriction that says do not repeat digits, then some of the 10,000 pins that we originally have to have repeats and we have to discard them. So now if we have this restriction that they can't repeat digits, we've only got 5,040 selections. All right, now let's give a different restriction. Let's say how many pins are out there that start with the number 3. So we've got 4 sort of moments. Let's think about this. Do we have any choice with this first digit? Well, we want it to start with the number 3. That means there's only one choice for the first digit. It has to be a 3. So this is going to be 1. Notice that when you're counting, when you have no options, that really means you have one option. You just have to pick that one thing. What about these guys? Well, it's not going to look like this. It's not going to be descending because there's no mention of repeats here. Instead, each of them is just going to be a 10. So this is going to be 10, 10, and 10. We multiply all those together, and we see that we get 1,000 different pins start with 3. And that should make sense, right? This 10, 10, 10 is really saying that if you have to start with the number 3, you're not really choosing 4 digits, you're really just choosing 3 digits, right? Because you only get to choose those last 3. So 1,000 different pin numbers start with 3. All right, now let's combine B and C together and ask ourselves how many pins are there that start with the number 3 and have no repeat digits. So once again, we get to make 4 selections. For the first one, we have to choose the number 3, so it's going to be only one choice there. For this guy here, we can't say that there's 10 choices because we can't choose 3 anymore. So there will only be 9 choices. Then for this guy here, there will only be 8 because we won't be able to choose the 3 and we won't be able to choose whatever we put there. And for the last one, we only have 7 because we are not having any repeats. We multiply that together and we get 9 times 8 times 7. And we should get that that is 504 different pins with that start with 3 plus no repeats. Notice that this guy is directly connected in value to this one because it involves the no repeats, but it is 10 times smaller because of the fact that we're not getting to choose that first digit. We're restricted to having to start with 3. All right, last one of these, just to, again, sort of really make sure we're comfortable with this. Let's see how many pins are out there that are palindromes. And palindromes just mean they read the same forwards as backwards. So an example of this, just to make sure we're clear on this, would be something like 3553, because if you read it this way, it's the same as reading it that way. Or, of course, something like 6666 would be a palindrome because everything's just a 6, so it doesn't matter which way you read it. So let's think about our choices. We've got 4 choices. We can choose anything we like for this first one. So we've got 10 choices. But remember, it has to read the same forwards as backwards. So whatever we put here has to be the same as what we put here. Whatever we put here has to be the same as what we put here. So we don't really have a choice with what to put here. Whatever we place here has to go here. So we've only got one choice for this guy here. For this guy, we can choose anything we like in the second one. So we've got 10 choices. Then, once we choose this guy, this has to be the same because they've got to read the same forwards as backwards, forwards as backwards. So there's only one choice for here. We multiply these together, and we see that there are 100 different pins that are palindromes. Now, this might be a little bit weird, but keep in mind that if you're going to have it read the same forward as backwards, you really only get to pick the first 2 numbers, and the rest of the password is determined for you. That's why the only parts that actually contributed to the answer came in those first 2 digits. So how does all this relate to probability? Well, one is it's going to be useful for calculating probabilities, but 2, you could also imagine these as probabilities. Well, how do we sort of use this? Well, we could say, what's the chance that you guess somebody's PIN number? Well, it would be 1 out of 10,000. What if you got extra information that their PIN number doesn't have any repeats? Then it would be 1 out of 5,040, and your odds would improve. If you happen to know that the person whose PIN number you were trying to guess was a palindrome, then your guess would be 1 out of 100, because there's only 100 different PIN numbers that are palindromes. So this is just to really help you guys sort of think about how we're doing this sort of counting. These sort of ones, this guy and this guy, should sort of stand out to you though, because we saw this sort of thing happen in that example about the sort of Democrats and Republicans and taking people out of the room. It's very sort of natural that every time you select somebody in one of those dependent situations, the number that remains is going down by 1. So this is a very sort of common thing we see in counting. So we're going to give one last set of definitions and then look at our sort of final example that really relate to this idea of counting things when you are not allowed to have repeats. Okay, a little bit of notation. Some of this, to be honest, since we're going to be using the calculator to take care of most of it, is not really necessary, but we're just going to mention it. So first thing we're going to mention, definitely not essential for our class, but probably interesting background information. We're going to define this little thing here called n factorial. It's written with an n and an exclamation part. You read it as n factorial, and it is defined as n times n minus 1 times ... times 2 times 1. So an example of that would be something like 5 factorial, which would be 5 times 4 times 3 times 2 times 1. And if you actually multiply all those things together, you would see that 5 factorial is 120. So factorial here just means you go 5, 4, 3, 2, 1. If it was 7 factorial, you'd go 7, 6, 5, 4, 3, 2, 1, etc. All right, factorials are interesting mathematically on their own, but for us, we're going to mostly use them to define two important things. So the first thing we're going to define is the number of ways to choose k objects from n without repeats, where the order of the selection matters, is called permutations. So we give this special name permutations to when we're trying to pick k things from n without repeats. And the order in which we make those selections matters. We call that a permutation, and we write it as npk. It's technically calculated as npk equals n factorial over n minus k factorial. You guys really don't need to worry about this definition because, as you can see down here, we're going to be using our calculator to take care of it. I'm just writing it out so that you guys can see it. Similar to this, the ways to choose k objects from n without repeats, where the order does not matter. So the big difference here is that the order matters in this guy. The order does not matter in this guy. This is called combinations and is written as nck. And here's its formula, but again, we're going to be using the calculator for this. Between permutations and combinations, mathematically, both are interesting, but to be honest, almost everything we're going to use in our class is going to be based on combinations. So this is the one you really want to be comfortable with. It's when you're choosing k things from n without repeats, and the order does not matter. In terms of calculator stuff, both of these can be calculated just by using your calculator. You don't need to worry about these definitions or this factorial stuff or anything. All you need to do is hit the math key on your calculator and then go to PROB. For older ones, it might just be written as PRB, and then you can find both of these operations. We're going to do an example on the next page to let you try that so you can try it on your calculator and make sure you get the same values as what we get in the video. Let's go ahead and take a look at this last example then. All right, so for this last example, we're going to still do some counting here. Let's just zoom that in a little bit. For this guy, we're going to count the number of possibilities in each situation. So in this first one, we've got someone has 15 different books. They're going to bring 6 with them on a trip. We want to know how many different groups of 6 books can they choose from. So let's think about the sort of different pieces of those definitions, right? Let's think about the total objects, the n. How many total options do they have here? Well, they've got 15 books, so n is going to be 15. Well, what is the k going to be? How many do they need to choose? Well, they need to bring 6. Okay? Can you repeat that? Can you bring the same book twice? Well, if you bring the same book twice, you're not going to actually bring 6. So, no, there are no repeats. Does the order in which you select them make a difference? Well, not really. If you pick one book before another one, you're still picking that book and you're still going to bring it with you, so the order doesn't matter. So what does that tell us? All of that tells us that this is going to be done using combinations, because combinations is what we use when the order does not matter. How would we calculate it? Well, we type in 15, then we go math, PRB or PROB, get the combination operation, and then put 6. And if you type that into your calculator, make sure you type in the 15 first. So put in 15, then hit that math key, go over to PRB or PROB, go down to where it says NCR, hit enter, and then hit 6, and then hit enter again. And you should see that it's going to come out as 5,005. So in other words, there are 5,005 different groups of 6 books that this person could choose from. All right, let's try this again on the next one. The next one says that we've got 10 friends that run a race. They want to give a prize for first place, second place, and third place. How many different ways can they award these 3 prizes? So, total objects. Well, how many people are there to choose from? There's 10 people in this race. How many do they need to choose? Well, K would be 3. Can you have somebody win first place, second place, and third place? No, everybody has to win their own prize, so there are no repeats. Does the order matter? Well, yeah, it makes a big deal here. If you win first, that's a different experience than winning second or winning third. So the order matters. So what does that tell us? Well, no repeats and order matters. That tells us that this should be done with permutations. So to do this, we would take the total number, 10, then go to our calculator and use math PRB and put the P operation, the permutation operation, and then 3. So to type that into your calculator, go 10, and then math, across to PROB or PRB, go down to NPR, hit enter, put in the 3, hit enter again, and you should get that that is 720. So there are 720 different ways that they can award first place, second place, and third place. All right, let's try the next one. A school club has 20 members. They need to select a president, vice president, treasurer, and secretary. How many different ways can they make these selections? So total objects here, n equals 20. There's 20 people in the club. How many do they need to choose? Well, they need to choose a president, vice president, treasurer, and secretary. So they need to choose 4 people. Obviously, there can be no repeats. You can't have the same person be the president and the vice president, so no repeats. And does the order matter? Well, again, it's a big deal if you get chosen as president versus you getting chosen as treasurer. And it makes a difference to you if you get chosen as vice president than if you get chosen as secretary. So the order matters. Order matters. That tells us that we can do this using permutations, and we should calculate it as 20p4 because we've got 20 total objects, 20 people to choose from, and we need to choose 4 of them. So we can do that, put in 20, then hit math, PROB, go to NPR, type in the 4, and you should get a very large number, 116280. So we're saying that there's 116,280 different ways that they can pick their president, vice president, treasurer, and secretary. All right. Last one here. We've got the same club. So the club has 20 members, and they need to select 4 people to go to a conference. How many different groups of 4 people? So total objects, n equals 20 still. They still need to pick 4. No repeats. Why no repeats? Well, because if you choose the same person twice, you're not actually sending 4 people, and they want to send 4 people. And does the order matter? Well, not really. If you're chosen first, second, third, or fourth to go to the conference, you're still going to the conference. So order does not matter. That tells us that this is done via combinations. So we've got 20C4. And if we type that in, 20 math C4, which is 4,845. Now, I wanted you guys to sort of see this, not because we're going to be doing problems like this. You guys really shouldn't expect to be asked to do a question like this, because again, our class is about probability and statistics, not counting. But I really wanted to, A, make sure you guys had some examples here to type into your calculator and make sure you're comfortable with this. And B, also just show you the difference, especially in C and D here, of the difference that the order mattering or not mattering really makes. Notice that when the order matters, it's a much larger number than when the order doesn't matter. And that's because if you imagine we've got, say, 4 people, just give them our standard names, Aaron, Bob, Carly, Danny, right? Then it's very different if Aaron is president, Bob is vice president, Carly is treasurer, and Danny is secretary, than it is if Danny is president, Carly is vice president, Bob is treasurer, and Aaron is secretary. But if those 4 people get selected to go to the conference, it doesn't matter if what order they were chosen in. So Aaron, Bob, Carly, Danny is the same as Carly, Danny, Bob, Aaron. It doesn't matter. That's why there's so many fewer options here, because a bunch of the groups are all the same because they're just different orders. So combinations are always much smaller in amount than their corresponding permutations. In the next video, we'll actually start to see how to use this to solve probability questions. And as we will see, it's going to be all based on these combinations. That'll be the one that's really important to us.